So, hello all. This is Vikram, finally a dual degree student at the Department of Civil Engineering, with specialization in hydraulics and water resource engineering. So, I'm a student of IIT Kharagpur, and today we'll be having a brief discussion about statistical models for extreme values analysis. So, this is a part of machine learning for a system sciences course, which I've registered in my this semester. So we'll be having a brief discussion on extreme values analysis right now. So beginning about the objective of this talk. So we'll be discussing mainly the statistical models for analyzing these extreme data values for any variable of interest. And also we'll be having an introduction to extreme value theory, and also we'll be discussing about generalized Pareto distribution and some discussion on this return period and return levels. So we'll be going through all of this. Um, Firstly, talking about these two main approaches that exist for modeling these extreme values, which are namely block maxima, and then the other one is threshold exceedance. So, brief about this, the block maxima approach was the first one, the first to be developed. But nowadays, like the threshold exceedance is the most commonly used approach among these two. And these two approaches have this one thing in common. So they both assume that the observations are independent and identically distributed. So this is the one observation that assumption that they have in common. And now talking about elaborating this block maxima approach. So it consists of dividing the observation period into non-overlapping periods of equal size. So what we do is we divide the data. Let's say we have any data for over the course of time. So what we do is we divide into equal periods of time, and then we pick out the maximas, which is like we restrict our attention to this maximum observation each period, and then we model these maxima through this generalized extreme value distribution. So we'll be discussing about generalized extreme value distribution, about its distribution function, and all. We'll be going through that in a while. So to make things more clear, we'll be using this. We'll be illustrating the block maxima and then the threshold exceedance by using this sample data. So this the data is a daily rainfall accumulation data, which is observed at a location in southwest England, and which was recorded for over the period of 1914 to 1962. So this is a freely available data in the R language if you have worked in that. So it is freely available in SMAV package in R. And so yeah, so visualizing this block maxima approach. So let's you can see the data is distributed in into blocks. Like there are blocks, the data is divided into various blocks. So here then we have taken a block of 1 year, like each block corresponds to 1 year. So generally we do take this annual maximum very often. It does have a plus point that it removes the effect of seasonality from the data, so that we can work on maxima without thinking of the seasonality or the effect of it. Okay. So after picking up the maximas from those each blocks, then we fit those maximas in this generalized extreme value distribution. So talking about generalized extreme value distribution, so it goes like this. Like, let's say we have m1, m2 up to mn random variables for a cluster of maxima from n time blocks. So the generalized extreme value distribution can be used to model these maximas, and it is given as gx equals to exponential of minus 1 plus epsilon bracket x minus mu upon sigma whole to the power of 1 by epsilon. So In this function, the mu corresponds to this location parameter, and it has a range of minus infinity to infinity. It can vary in that range. And the sigma, which is a scale parameter, so uh, it can vary from 0 to infinity. And then epsilon, which is the shape parameter, and it is a very important parameter in this distribution. So it varies from minus infinity to infinity. So talking about these parameters, so the shape parameter epsilon is a very important parameter, and as I earlier said as well. So it is very important parameter, and it does control the heaviness of the tail. So it directly affects the extreme, and we can see that if epsilon is greater than 0, so it has a very heavy upper tail, and it corresponds to Fletcher distribution. And if epsilon value is negative, less than 0, so it has a bounded upper tail, and it corresponds to negative Weibull distribution mainly. And uh, when epsilon is equal to 0, so it has an exponential upper tail, and it corresponds to Gumbel distribution. We'll be going through it again through a diagram, so that we can have a better understanding in a while. Now talking about the return levels, so uh, the thing is, like, we are interested whenever we model these extreme values, we are interested in estimating the severity of extreme events. So uh, let's say we are talking about an event that happens in once in every t years. So in other words, we can say that it has an annual exceedance probability of 1 by t. So uh, the return level zt corresponds to uh, the value that it can exceed in t years. Uh, so here is an equation that is given to calculate the return level with the return period of t years. So the return level is given by when epsilon is not 0. So return level zt can be calculated as mu minus sigma by epsilon bracket 1 minus log of 1 minus 1 upon t whole to the power minus epsilon. And when epsilon is equal to 0, so the zt is equal to, the return level is given as mu minus sigma log times log of 1 minus 1 over t. So earlier we talked about this shape parameter, how this affects the tail. So we can see uh, when these values, like the black line corresponds to the case when epsilon is 0, and red line corresponds to the case when uh, epsilon is positive, and then this blue line corresponds to epsilon less than 0. So we can see this blue line corresponds to Weibull distribution, and this uh, black line corresponds to Gumbel distribution, and this red line corresponds to Fresher distribution. So this is the graph for the return level curves, and this is for a GEV distribution function. So now we have talked about this block maxima approach. Now we'll be discussing some points about threshold exceedance approach. So in this approach, what we do is we fix a threshold value, and we take values that are above those that threshold, and to model with our GPD distribution. We'll be talking about that in a while. So what we do is we fix a threshold, and then we take data uh, lying above the threshold. So to model that, we use generalized Pareto distribution, and it goes like this. Like, let's say we have x1 x2 up to xn, a sequence of random variables, then the distribution g of exceedances over high threshold is given of the form g of x is equals to 1 minus 1 plus epsilon of x minus u upon sigma u whole to the power minus 1 by epsilon. So here for x greater than u, we have this sigma u, which is the scale parameter, and it has a range of 0 to infinity. Sorry. And we have this epsilon, which is the shape parameter, and it ranges from minus infinity to infinity. So we'll be talking about this parameter. So the scale parameter here is a threshold dependent. So for any threshold that is v greater than u, so we modify it like this. Sigma v is given as sigma u plus epsilon v minus u. And the shape parameter of GPD is similar to the shape parameter that we discussed earlier in this, that GEV distribution. So it is more or less same. Now the thing is, like we talked about this threshold exceedance. We said that we set a threshold and we model values that lie above the threshold. So the thing here comes is a problem here comes arrives, like how to choose that threshold. So we can use this bias variance trade-off to choose an optimum value of threshold. So let's say we have if we set a lower value of threshold, then we'll be having uh, like a lot of data to model, but that model may not fit on those low values, because we have developed our models for modeling extreme values. So concluding that, like if threshold is too low, then we may not have extreme data model, so model will not be suitable. And if we set the threshold too high, then we may not have this enough data to work with, and there will be high uncertainty involved. So talking about return levels corresponding to this GPD, and it is more or less same as we discussed in that GEV theory. The only difference here is we have used this m in this equation. So what is m here is, m is given as nt times t, where nt is defined as the number of observations in a year. So the equation goes like this: the m observation return level is given as zm equals to, when epsilon is not 0, so zm is given as u plus sigma u by epsilon into m sigma u to the power epsilon minus 1. And when epsilon is equals to 0, so zm is given as u plus sigma u log m lambda u. So this is the theoretical part that we have discussed till now. So here is a worked out example that I have worked earlier. So this was a work carried out by me during my bachelor's thesis project, which was done under the guidance of Professor Saud Afzal, which is a professor at the Department of Civil Engineering, IIT Kharagpur. So what we did was, we had a study location of Mehamn Harbor, Norway. So we had a data from uh, September 1st, 1957 to May 31st, 2017, which was roughly like 60 years data. And our main problem, the problem statement was, we were to calculate these extreme values uh, that any coastal structure built at that place will face during its lifetime. So we worked on that problem. So we used this extreme value distribution there. So uh, we will firstly talk about the data that we use. So to visualize the data, so you can see the highest frequency the data has is from a range of 0 to 4 meters at all. So but our main approach was to model the wave heights that corresponding to height of 8 meters, or like above 6 meters or so. So mainly we had to model the tail of this density distribution. That was our main task. So what we did was, we took this data, applied this block maximum approach. So we made 60 blocks, which corresponding to each year. So we divided the data into 60 blocks, and then we picked out the maximas from each of these blocks, and those are segregated to for model fitting. And so here also we use those annual maximas so that we don't have this effect of, we can neglect that effect of seasonality uh, in our data. So this is the thing. And these the data of the maximas from each block were taken, and then they were modeled with GEV distribution, and we used maximum likelihood estimation to yield the values of epsilon, mu, and sigma for this GEV distribution. So the value that we got was epsilon corresponded to minus 0.054, mu value came to be 7.432, and sigma value came to be 1.124. So as we earlier discussed, the epsilon value is a negative one. So the distribution that we will be getting here will be a Weber distribution. So will be which is in in sync with the results that we have got. I will be showing that later. So the methodology, as I earlier told, so we calculated those GEV parameters, and by calculating the values of epsilon, sigma, and mu, so we put those into this equation that corresponded to calculate the return level. So we put those values in this equation, and we got return levels for each time period for 1 year, 2 years, and correspondingly 50 years and 100 years, for uh, which is an average life of a coastal structure we were interested in. So we calculated that. So here are the results, and you can see it corresponds to a Weibull distribution, as the epsilon value that we got was negative. So it is in sync with those results. That's the thing. Okay, so that's all from my side. Hope we'll be meeting soon.